Without further ado, Paul will tell us about the variant of monotone calculus.
Okay, so I'll be talking about the variant of monotone calculus. I was originally planning to give a blackboard talk, which almost happened. So the way how this, I want to introduce some proofs and say something about it. The reason why I'm interested in is the following. I like proof complexity on one hand and arithmetic circuit complexity on the other hand. And it's fun to see where the two things can possibly intersect. It's like in this fairy tale when dog and cat were making a cake, and both of them put like the things that they like in it, like mouse and salami, and it was a lovely cake, and they got really sick afterwards. So that's proof complexity and arithmetic circuit complexity. So it's the wrong way. They didn't eat it. I know it's more complicated. There was a bad dog who came and ate the cake instead, and the dog got sick. But then you would ask the question, which the dog? And
the fairy written by a Czech writer, probably nobody in the audience except like 3 people know.
That's why I didn't want to get into it. But thanks for the Anyway, so the basic setup is the following. You have a monotone circuit, meaning a circuit monotone polynomial, which is a polynomial with real non-negative coefficients. That's what the monotone polynomial means for you. And let's denote the support of f be just a set of non-zero set of monomials with non-zero coefficients. So say if you have like 2x squared plus yc, then the support of these is just the set x squared plus the support. And now you would like to ask the question, when is the support of one polynomial contained in the support of another? The simple observation that will make sense is the following. So if you have a monotone polynomial g, then the support of f is contained in the support of g if and only there is some epsilon non-zero such that g minus epsilon f is non-negative, is monotone. Okay. Why is this so? Well, if you have this guy and you are trying to subtract from it something which has a different support, say we're trying to subtract the polynomial x plus yz, then this x will have always a negative coefficient. If you are subtracting some non-zero multiple of this dude from that dude, it will never be one. And conversely, if you have something with the same support as this, let's say 10x squared plus 5yc, you can just scale this guy down so that when you subtract it from this guy, the result. So that's a simple relation. Now, and let's make this a proof system. So I will say that well, an AMC proof that I guess it's a highly creative title. I guess it stands for arithmetic and monotone calculus, is a monotone arithmetic circuit that actually proves G, computes G minus epsilon. So I haven't defined what an arithmetic circuit is. It's just a model of computation when you start from variables and you add.
Let's see. Is there an issue that like if you have like x squared next to the fourth, then you could subtract the small multiple.
Yeah. So that's important. So like if you live in the Boolean world, then x squared and x to the fourth take the same value on the cube. But as a polynomial, those are distinct polynomials. So, and for me, these two guys are very different polynomials. So it's not true that x squared is contained in x. Support of this is different from the support. If that was your question.
As further asking, like if we look at say x squared plus x to the fourth minus epsilon times x cubed.
That also wouldn't work. Like the support of x squared is just x squared. If that answers your question. So forget about the Boolean values. Think about what these dudes do on like the whole set of real numbers. If you want to think about it as a function. But for me, it's just a syntactic object, like the formal product of variables. And I don't really care what these guys do. So I don't care.
Okay, actually, so he just said. Reminding me like the definition of monotone here.
Okay. Yes, I haven't said it yet. So monotone polynomial is a polynomial with non-zero, with non-negative coefficients. So like x squared minus 0.1 x cubed is not a monotone because it has a negative coefficient. So like monotone polynomial means that all the coefficients are non-negative. And the monotone circuit, which is important here, is an arithmetic circuit which uses only non-negative real numbers as constants. So in particular, it doesn't use any form of subtraction. So arithmetic circuit just starts from variables and real coefficients and computes other stuff by multiplying and adding. So that's a circuit. It looks like a Boolean circuit, except that the basic operations are addition and multiplication. And monotone means that you don't use negative numbers and you don't use subtraction.
How do you know it computes for a proof G minus epsilon?
Yes, okay, so that's my definition, if it makes sense. And now, why is it legitimate to call this a proof system? So let's say you have H, which actually is this G minus epsilon. And let's say you completed it by a monotone arithmetic circuit. So this is given by a monotone circuit. The fact that it is computed by a monotone circuit is just a syntactic thing. Just look at the circuit, you see what numbers it uses. You can check if it's monotone. And to see that it's actually a correct proof, you have to check that this equality holds, where I'm assuming that both G and F are also given by some sort of a circuit, which doesn't necessarily have to be monotone. But this is a polynomial identity. This is an instance of PIT, which we don't know whether it is polynomial size algorithm, but by Schwarzschild and lemma, which is being constantly renamed to something more complicated. This is efficient randomized. So that this proof is correct, you can check it efficiently, at least by random.
But that is if it is integer coefficients. You said the coefficients can be arbitrary reals.
Yes, thank you. So that's another question that I didn't want to get to. So there was the dot in the size of the question. So yes. Okay, let's make this epsilon to be represented as a rational with like a small binary representation. Good.
Can the coefficients on F and G and H be real?
The coefficients of the circuit itself.
Yes, and the coefficients of the circuit itself. Okay, there are at least two. There are several mutations of this system. How you can look at it. So one of them is, but it's not just my problem. It's the problem of the whole field of arithmetic complexity. So do you measure the size of the coefficients on Okay, for me, it's mathematically cleaner not to measure the size of the coefficients and just be them given for free, which however implies then what I just said about PIT makes no sense. Or there is the alternative approach of just representing the coefficients as rational numbers in some reasonable bit of some reasonable bit size. Then what I said about PIT is true, but it becomes mathematically less elegant. So it's a bit of an obfuscation. Okay. So how is this related? Well, to more traditional DNFs, let's say. So suppose you have a DNF in variables x1 through xn. So I can make out of it a monotone polynomial. The way how you can do that is the following. So we introduce new variables and their negations. So instead of n variables, you will have two n variables. And you introduce this funny polynomial. If this doesn't make much sense, note that the monomials of this polynomial can be identified with the Boolean assignments to the original variables x1 through xn. So this big product over n either has x1 0 or x1 depending on whether the Boolean assignment you are talking about assigns the variable x1 to 0, 1, etc. So it's the big product just represents a Boolean assignment, and the coefficient of each monomial corresponds to just the number of clauses of the original DNF that are satisfied by the given truth assignment. That's the definition. It doesn't seem maybe the most natural one. The reason why this makes sense is that this high of D, this polynomial, has a small monotone circuit, which is very easy to compute. If you think about it for a little bit from the DNF representation, D, you can easily construct a very shallow sigma by sigma circuit that computes this polynomial. So this is a very easy to compute. Now, if you sort of unravel this definition, what happens with it if you apply it to just the DNF, which is identically 1, which is 1 term, which is the constant 1, then you get this product, or in fact, like the sum over all truth assignments. Before Emil says anything, of course, this definition depends on like what space of variables I'm dealing. But the DNF, which is identically, which is just 1 term and it's equal to 1 always, is just a big product list. Another simple observation is that if D is a tautology, if and only if every monomial that corresponds to a truth assignment appears with a non-zero branch. It just means that this polynomial corresponding to constant true, the support of it is contained in the DNF, in the polynomial corresponding to medicine. And that's pretty much everything I know about this system. And I'm interested in proving something non-trivial about it. So there's only one thing, and an AMC proof of this D would be just this high of D minus epsilon times high of 1. And you are supposed to compute this by a monotone circuit. And you are interested in the size of the circuit. Well, the only sort of non-trivial thing I can prove about this system is that it's at least a strong resolution, which is not a hard proof. And what I'm really interested in is the following two open problems. And the first one is to prove a lower bound on this guy. And the second one is to see whether it simulates Frege or not. Now, ideally, of course, it would be really exciting if you could solve both of these. Well, depends how you solve it. Probably it does not simulate Frege, and then you prove a lower bound. The natural way how to do it. Of course, the reason why I'm laughing is it's nice to prove a lower bound and show that it's simulates. So those are my open problems. So I guess I'm over time. Can I say?
You until 12.
Oh, okay. So let's go back and I thought I end up at 1.5. 11. Okay.
Can I ask a
Yes.
question? Does this simulate trolley hugs?
No, well, I'm not aware of it.
Okay.
But it's a good question.
It's very close to this like minus, this separation complexity stuff.
Yeah.
Yeah.
So, why is the talk called a variant of monotone problems? So there is a thing which is closely related to this, and that's the monotone problems, which I believe was defined by Albert, Nicola, and Pavel.
Pavel defined it before.
Okay,
You studied it.
okay, perfect. So that's a version of Frege where you are proving implications of this form. A implies B, where both A and B are monotone formulas. That's the system they study. And in fact, they define it as a version of a sequent calculus. But the point is that here you have only one non-monotone connected, which is the implication. Here you have only disjunctions and conjunctions. Here you have also only disjunctions and conjunctions. So that's the system they care about. And they proved that this thing quasi-polynomially simulates a Frege system. And if you look at some sort of extended version, or if you allow this system to work with circuits, monotone circuits instead of formulas, this is actually equivalent to extended. So having monotonicity of this form is not a serious restriction on the system. Now, the system over there, even though it may not look that way, is in fact weakening this system. And because instead of this epsilon f minus g, one could also form some sort of a more syntactic version of this, which would look something like this. You would have basic axioms which say that f, well, that system, if you want to open it, would be proving implications of the form that support of f is contained in the support of g. And you could add, you could start with axioms of this form, that the support of f is contained in the support of f. And then you could have rules which says that, let's say that if f1 is contained in g1 and f2 is contained in g2, then you could conclude that f1 plus f2 is contained in g1 of g2, and similarly for multiplication. And then you would probably add another rule which says that if f1 is contained in g and g is contained in that f1 is contained in f2. So those would be the rules. And it can be shown that somehow this ACM system is like all of these rules together, like compressed in one single thing, which I will not get into. So this will be like the syntactic version of this ACM system. Now, when you think about it a little bit longer, this is pretty much this monotone calculus, except you have removed certain Boolean rules, which goes back to this question. So in this system, when you understand addition as disjunction and multiplication as conjunction, so in the monotone calculus or in propositional logic, you can prove that X implies X and X, or you can also prove that the conjunction of X and X implies X, which corresponds to sort of, I guess, left weakening and left contraction in the Gensen-style symmetry. But these two rules cannot be implemented in this system because in terms of the interpretation of the support of a polynomial, this would amount to saying that the support of X is contained in the support of the polynomial X squared. And similarly, this would amount to saying that the support of X squared is contained in the support of X, which in the interpretation through polynomials, this is not true. But so you can think about this system as a weakening of the monotone calculus when you remove these Boolean roots. So for this reason, why shouldn't we be able to prove lower bounds of this? Because it seems like a weaker system than monotone calculus and hence Frege. So that is my motivation.
Monotone calculus is a Cook-Rekha system, this is not.
Excuse me?
The monotone calculus is a Cook-Rekha system, but this one is.
Yes, yes, I'm hiding some things under the rug. Yes. Okay, that's all. Say thank you for your attention.